Pertanyaannya adalah, seberapa dini kita mampu mendeteksi warning sign tersebut sebelum berkembang menjadi failure? Nah, melalui webinar hari ini, kita akan bersama-sama memahami bagaimana menentukan strategi monitoring partial discharge yang optimal mulai dari periodic inspection hingga continuous online monitoring. Nah, kita juga akan melihat bagaimana pendekatan monitoring yang tepat dapat membantu meningkatkan aset reliability, meminimalkan outage, serta mendukung implementasi predictive maintenance. Baik, sebelum kita mulai webinar hari ini, saya juga mau menginformasikan kepada Bapak Ibu sekalian, jika Bapak Ibu mau mengajukan pertanyaan, silahkan dapat langsung menuliskan di pertanyaannya, dituliskan pada kolom chat ya Bapak Ibu. Pertanyaannya bisa lebih dari satu tentunya, dan bisa juga langsung dengan bahasa Inggris atau bahasa Indonesia, nanti akan saya bantu untuk translate-nya. Dan speaker akan menjawab pertanyaan-pertanyaan terpilih setelah selesai menjelaskan materinya. Dan Bapak Ibu juga bisa dapat bertanya secara langsung nanti di akhir ya, dengan menekan tombol raise hand dan menunggu sampai dipersilahkan oleh saya untuk bertanya dengan mengaktifkan video dan audionya. Jika audio udah pasti ya Bapak Ibu, kalau video jika memungkinkan saja kalau memang sinyalnya mendukung gitu, karena biasanya videonya agak susah ya kalau sinyalnya tidak terlalu baik. Baik, dan informasi yang berikutnya, di webinar kali ini kami menyediakan 4 giveaway bagi peserta yang beruntung. Untuk 2 giveaway untuk kategori peserta yang aktif bertanya selama sesi berlangsung, dan 2 giveaway yang berikutnya untuk peserta yang mengisi feedback form yang akan dikirimkan oleh tim dari PT Tiara Vibrasindo di akhir acara. Jadi untuk webinar hari ini kita akan mengundi 2 peserta dulu yang aktif bertanya. Kalau untuk yang peserta yang mengisi feedback form itu diundinya besok, karena mungkin Bapak Ibu membutuhkan waktu untuk mengisi feedback formnya setelah acara ini. Dan besok akan kita undi di Instagramnya Tiara. Jadi jangan lupa untuk follow Instagramnya PT Tiara Vibrasindo supaya bisa update apakah Bapak Ibu menang di undian feedback form yang sudah Bapak Ibu isi hari ini. Oke. Alright everyone, thank you once again for joining us today. With that introduction, let us move to the main session. And I'm delighted to introduce our speaker, Mr. Andrew Swan from EA Technology. Hi, Mr. Andrew. It's great to have you with us today. Mr. Andrew, how are you today?
Hi, I'm good. Good afternoon, everyone. Thanks for inviting me and to present this topic. I hope this topic will be helpful to those who have attended. Yeah. So
Sure.
yeah. So can I start sharing my screen?
Yes, sure. Take your time, Mr. Andrew. Thank you.
Okay. I just want to confirm everybody can see my screen.
Yes.
Okay. Okay, so I just want to emphasize again today's topic. Today, I think PD, partial discharge has been maybe a common topic to all of you that have attended. Yeah, so every time when we talk about PD, a lot of time the customer will ask, oh, got PD. So when will my instrument fail? So that's always the most challenging questions that I know as an engineer we got to answer to our customer. So it's just like today, you got a heart problem, and the doctor said, yeah, you may have heart attack anytime, but the doctor will not be able to tell you when you're going to have the heart attack. So I think it's the same for PD, because PD is at this stage of time, it's still very intermittent. So today, my sharing will be like, how can I like minimize and then confirm, so that I catch the PD before it fails. So that is the whole so-called the main topics that I want to be talking about. So that's why we call it the optimizing partial discharge testing strategy for your high voltage asset reliability. So it's a strategy that help you to maintain your assets reliability, make sure that you are always on. You don't want to have any unplanned outages. Okay. So this is a quick introduction of myself. Okay, this photo taken maybe 10 years ago. Hopefully now I have more gray hair. Yeah. So basically I'm more of a sales engineer. So for what I do has been going around Southeast Asia with EA Technology to provide asset management solutions from PD, MV assets all the way to LV assets now. That's what I've been doing for the past 14 years with EA Technology. Okay, so today I prepare four pointers or four chapters of sharing. So first one I want to just to make sure that everyone is clear PD and how we classify it. Then we talk about the point to failure curve from the day you find PD and then to the day it fails. So there's actually a study about this P to F curve. So I just want to talk a little bit about that one. Then I give you some case study, some real life case study. And then lastly, we talk about the probability of early detection. That's I think what we want. We want to detect PD early. But how early is early, then later we'll discuss a bit more. Okay? With that, I'll go into the today's slides. Okay, PD classification. So those who are very well versed or have experience with PD, so maybe you just have to bear with me for a while. I will quickly go through. This is just for the benefit of those who are new to partial discharge. Okay, so in the world of PD, there are a few classification. First one, of course, is a very common one. Is the internal PD. Internal PD basically is something like a void in the insulation. We can't really see it with our own eyes. If there's some void, this kind of void can be due to poor QC. When the manufacturer make the insulation, when they melt the rubber, sometimes air bubbles go in. So when the rubber or the insulation harden, there's a void being formed caused by the air bubble. Okay, so then it actually cause an internal discharge when high voltage, so-called the high voltage stress across the insulation. So this one will cause internal PD. So internal PD, a lot of time we make use of the transient voltage sensor to pick it up. Okay, so that's internal PD or internal discharge. Next, we have the surface discharge. So surface discharge basically is something that we can really see. In fact, we can see and sometimes we can even smell it. Okay, and we also can hear it. So this surface discharge is something like you see in your insulation. There are some electrical trims, some cracks, some corrosion happening. So these are surface discharge. And when there's a surface discharge, right, basically it generate ultrasonic sound energy. So unfortunately, our ears are not tuned to the high frequency. We cannot pick up the sound by ourselves. So we need to depend on equipment, to pick up this high frequency sound signal. And for us to then decide whether is this a real PD or is this a noise. Okay. And number three is corona discharge. Corona discharge is actually a discharge from a sharp angle. So this is actually, if it's discharged to the air, and then it's harmless. But if it's actually discharged to the surface, then it may cause problem for you. So in a lot of I think it's very common in open switch yard. Sometimes when you walk across it, you actually hear some loud crackling sound. A lot of time they are actually corona discharge, and then this discharge are actually going through to the air. So once the energy bursts through the air, a sound energy is being generated. You hear some loud crackling sound. But if it's to the air, then it's actually not a cause of concern. But if it's actually pointing to another area or a switch gear, then you may want to be, that may actually cause some problem later. Okay. Last but not least, we have this gap contact floating metal. Sometimes if your contacts or your surface are supposed to be tight, but then because you did not tight it tightly, and then there's gap, and then this will actually also cause a PD to happen. So we call it the contact gap floating metal. So basically, these four pictures sum up the type of PDs that we always see in our day-to-day work. Okay. So internal discharge, how does it look like? Okay, we actually from our, for EA Technology, I think we have been working with PD for 60 years. In fact, this year we celebrate 60 years in the business. So with all this experience and then from our database and from our day-to-day course of work, we more or less can actually identify what type of PD is this by looking at the PRPD plots. So each cavity can give a different phase resolve patterns. So different type of problem will actually demonstrate different type of waveform pattern in the PRPD plot. Okay, so but of course the main thing that we really want to see is there are actually two cluster 180 degrees apart. So this is the main thing that actually help us to identify, is this a real PD or is it a noise? Okay, so these are some of the patterns for internal void. A lot of time we will say it looks like eyebrow, the shape of eyebrow. Some people say, oh, maybe look like the shape of shark fin, yeah. So these are some common shape people use to identify PD, okay, for internal discharge. And then surface discharge is something that is more interesting. It actually looks like a hump. Sometimes we always say it looks like a camel hump. So when there is actually a surface discharge and your sensors pick it up and then they are able to plot it out in PRPD plots like what you see here. A lot of time you see two hump 180 degrees apart. So that one more or less will tell you that this is actually a real ultrasonic sound coming from a surface discharge. Okay, so that is roughly the shape and how it looks like. Next, the corona discharge. Like I say, this corona discharge is basically, if you pick it up, it basically just a single hump. So if you remember what I said just now earlier, for surface discharge, there's two hump being formed, okay, 180 degrees apart. But for corona discharge, it's only a single hump, okay, and then this is how it looks like. And then if that's why in the course of work, you hear some loud crackling sound, and then there is only a single hump in your equipment. Then if you look at the discharge direction where it's coming from, then you roughly know whether this is a corona discharge or not. Okay, I've actually prepared a sound file. Let me see whether y'all can hear it. Can you hear it?
I don't think so, yeah, Mr. Lily.
Oh, okay. Let me just try again. See what I can do. Record up. Let me share computer sound. Okay, I think can already. Let me try again. Okay, so this is the typical sound of a corona discharge. Okay, yeah. Okay, so basically, I have quickly sum up to you what is actually all the different type of discharge. And so when you have PD, these are some of the things that you will see on the equipment. Okay, so the next thing is we always like to ask, the probability to finding and acting on a PD defect before failure. So that is the question that I first posed at the beginning. Every time in the course of work, I share with my customer, oh, your switchgear have PD, uh, your transformer have PD, and then the customer will always ask, oh, so when will it fail? How long more time do I have? That will become a very typical questions that customer will always like to ask. And in my earlier stage of work, I actually came across a very senior engineer. So when he actually answered this question, and I think it's a very good reply, because when he said when my equipment will fail, and you guess what is his reply? He said, "Oh, only God will know." Oh, so the customer was shocked. Huh? How come like that? Why you don't know when you'll fail? Okay, so that was actually the very beginning stage when we are actually, discovering PD and try to know how bad is the impact to our instrument. But today, I think as the increase with the technology, we are able to now make more knowledgeable and more control assumption when the instrument may fail. Okay, so that's the purpose of this P to F curve. Okay, so this P to F curve is actually the probability to finding and acting on a PD defect before failure. So that's, I think, what we are all interested to know. Okay, so let me quickly go through, this how you operate this P to F curve. This point is where failure start. Okay, but when a failure start, it can be so small or that your instrument can't even detect at the moment, okay? Because the PD may be very small PD, just starting. So the transient earth voltage, the ultrasonic sound that's being caused by PD is so small that can't be picked up or sometimes even masked by the noise. Okay, so this is the point where failure start, but the time to detection, it will take time. So sometimes it may take months, sometimes it may take weeks, where the instrument start able to pick up the signal from the PD. Okay, so the point where you're able to pick up this is the P. We say this is a point where I can detect the failure, detect the PD already, and then I will then tell myself from this point where I can detect to the point of failure, how long? Okay, how long? How much time I have? Do I have enough time to wait for the next shutdown, or I need to quickly, de-energize the machine and then open up and see what is the problem? If I don't do it now, maybe tomorrow it will flash over. No, is that how serious? We don't know, right? Every time when this kind of situation, we are all guessing and we are not sure. But today is different. Okay, so every PD defects have a unique P to F curve that is dependent on a few characteristic of few factors. Yeah, so I would say every PD is special. It won't be the same, every time you see it. So it depends on the type of PD, like what I share with you. It can be internal discharge, it can be surface discharge. And then if it's coronal discharge, then it's good because if it's discharging to the air, then we do not have a concern. Yeah, but if you're actually pointing to my bus bar, then maybe there'll be problem. Okay, so first thing you determine what type of PD it is. Then you try to know it is on what type of HV asset. Is it on my cable, or is it on my switch gear, or is it on my transformer? Then you may want to go even deeper. Which part of the transformer? Is it inside the oil tank, or is it inside the cable termination? Okay, so this one will also determine how fast or how short the P to F interval is. Yeah, okay, so that is the type of assets. And then if it's a cable, then you may want to ask, is it a paper cable or is it an XLPE cable? Because we all know, sometimes based on my experience, XLPE cable, the time to fill it is shorter compared to a paper one. Okay, depend on the different scenario. Okay, so that is, and also some brands, some certain model of switchgear, that I actually come across are actually known to cause more problem in their certain compartment. The brand that I get used to know is that in Singapore, certain brand, their HP always have problem. So every time we go in, first thing we check, okay, is this ABC brand? Then I will ask my engineer, please go and check on the VT first, because 9 out of 10 problem always come from the VT. So knowing type of HV asset also very important. Okay, and then number 3, the discharge amplitude. In EA technology, we have a guideline. Like you are using an instrument to pick it up, the same. Our guideline is from 0 to 19 or 1 to 19 is still considered still within, although there's PD, is still within the safe zone. Okay, and from 20 to 29, then is in the amber. Amber zone means maybe there's some form of defect already, is getting from bad to worse. You may want to take action ASAP. And then from 30 to 60, the color is red. Code red means danger. So a lot of time we see this, we got to inform the owner and quickly tell him, please make a decision soon. If not, you may experience unplanned outages because your switchgear may fail anytime. Okay. Then number 4, insulation type. Type insulation, just like what I mentioned earlier. Is this XLPE or is this paper? Okay, or is this SF6 or is this air insulated? So these are different type of insulation you got to take into consideration. Okay. Number 5, environmental conditions. Some of the switchgear, I mean, in general, our electrical assets are actually don't like high humidity. That's why in the modern switchgear substation, we install aircon, because we want to control the temperature, we want to control the humidity. So these environmental conditions are very important, especially in Southeast Asia where the humidity is high. So that's why when humidity high, you tend to have more surface discharge. Then sometimes you also want to know the location where your substation is built. Some of the substation may be built near to river. So sometimes if near the river, then of course the humidity will be much higher. Then you're actually more prone to surface discharge. Okay? And then some are maybe high up in the mountain. In the mountain, then the temperature change is very drastic. Sometimes daytime very hot, but at night it become very cold. And then you start to have condensation. So these are certain things that you also want to take into consideration. Okay. And then the physical position of discharge. You want to know where exactly the discharge happened. Is it in the circuit breaker? Or is it in the VT, CT chamber, or in the cable termination? Okay, so these are all the few things that we think is good for you to find out, this 6 point, then before it will actually contribute to the P to F interval, how fast the switchgear will fail or the transformer will fail. Okay, so understand this, then you get to be able to plot out the P to F interval time frame. Okay. Okay, so the next slide, the probability to finding and acting on a PD defect before failure. So that's, I think, what we want. We want to act before the switchgear fail, or before the switchgear flash over. We save the money. We just need to change maybe the parts that is have problem. If you don't detect in time the flash over, then you may need to change the whole panel. Okay, so for every defect, there are unknown factor. These are a few things that is beyond our control. We don't know. Example, you won't know at the point at which the failure first start. That means like when PD start happening, we won't know, because sometimes it's so small, sometimes we miss it because the signal is so small, our sensor cannot even detect it. It will miss out. Okay, the second point, the point at which the defect can be detected. So that is the time where we can detect. But being able to detect and being detected is another two different things. Because when, let's say, example, the point which the defect can be detected is in January. But in January, you are not there to do your PD survey. You only do that in June, 6 months later. Then you detect. Then basically, you actually wasted 6 months of detecting the failure. And then the time to failure, the P to F curve may be actually shorter, because maybe 9 months, that means you actually wasted 6 months. So now only 3 months left for you to do something before the thing happens. Okay? So giving this example, I'm just trying to tell you that the testing interval need to be designed to eliminate or reduce this unknown. Okay? So what thing I need to know? A lot of time when we started PD survey, or we engage our people to come to do PD survey, it's always on a what? Annual basis. So they say, one time enough lah, So this year no PD, then maybe next year I get the contractor to come and detect. But if you only do it annually, then high chance you may miss the point which the failure start, and then the point which the defect can be detected. Most likely you also will miss it, and then you only detect it at the final or the late stage. Okay, so this goes to this third point. The lower the testing interval, the higher probability of finding the defect early in the P to F interval. The early the defect is identified, of course, the longer the reaction time for the asset owner. I think that is understood, right? So the main thing is periodic testing will reduce unknown but not eliminate them. So that's the thing what the P to F curve trying to tell everyone. Okay, so let me just quickly show you the curve again. Follow me. So P, point at which the failure start. This is the point failure start, but still too small for us to detect. No, our signal still very small. Our sensor may not be able to pick up. So there's a time to detection. So from time to detection is where the P start. This is the point which the defect can be detected, but you may not be there to pick it up, because you only go back every year. So you may actually wasted some time. So depend on the type of failure. If it's out surface discharge, then the failure can be real short. Some as short as a few weeks. Yeah. So if it's a surface discharge, normally we always tell our customer, surface discharge is being detected. We confirm it's a real PD signal. So please take action ASAP. Why? Because surface discharge, the time to failure is very, very short as compared to internal discharge. Internal discharge, sometimes the failure, the point to failure interval can be quite substantial. When I say that, that means it can be months or sometimes even years before failure happens. Okay, so we got a longer runway to decide what we want to do next. Can we actually shut down during the schedule maintenance, and then we do a shutdown and then we change, or we have no time to wait. We need to take action ASAP. If not, this thing will flash over, maybe in a week's time or in 1 month's time. So this one is depend. Okay. So the point of failures also depend what type. So that is what I shared earlier. What type of PD and what is the consequences. And then another thing is you want to ask yourself, what is your risk appetite? Can you afford the failure? So maybe, yeah, if it's just 3.3, 6.6 kVs switch gear, maybe the impact is not so much. So then I can, afford to wait. Yeah, so that I will not cause a disruption to the production. I mean, some of y'all may be coming from a factory environment, oil and gas environment. If today there's an unplanned shutdown, I think there will be high costs incurred for the fail in the production. So that's why they always do not want to have a unknown shutdown. Or some may even wait or extend their shutdown from every 1 year. They say, hey, can we extend our shutdown to every 2 years or 3 years? So every 3 years we do one time. Yeah, so that is what people are trying to do. But of course, when the day you detect PD, then it reverses the question: is when can we shut down? It's no longer when can we extend, but when? How fast can we do the shutdown? You ask yourself. Okay. So that is the 2P to F curve. So today I want to share with you, some case studies. So these are some real life case studies that happened, and then from there I will try to show you how to relate this case study to a P to F curve. Okay. First one, very interesting. This one happens in international airport in Australia. Last year, there's a lot of very high profile failure recently in the airport. I think the last one was Heathrow, where Heathrow Airport have a major power outage. The whole of Europe is impacted because Heathrow in UK is one of the busiest airport in Europe. So a lot of flight was cancelled. A lot of flight was actually divert from Heathrow to another airport. So they cause a lot of inconvenience and of course a lot of revenue loss. So this happens to be a 11 kV RMU, ring main unit. Okay, so happened in Australia. Australia is also a place that we have an office, so we work there quite regularly. So this customer always invite EA to do every year do a PD survey. Okay, and then recently they on the year they say, oh, our RMU very old already. It's an oil field RMU. So we decided to change to a new RMU, the SF6 RMU. So although they changed the new RMU, but unfortunately they did not replace the cable termination. Instead, they used back the old one, the old cable termination from the oil field RMU. So this was the root cause of the problem. So the new RMU was tested yearly for 4 years. No issue, new RMU, right? People say, oh, my asset is new, so should not have problem one. So for the first 4 years, no problem. Okay. On the 4th year, 4 year for RMU is still considered very new, but we start detecting a low level of PD source. And then from being detected to the thing fail, only 7 months. Okay. So this RMU failed within 7 months of detection. So some of y'all may ask, hey, Mr. Andrew, if you detected, how come it still failed? Well, a lot of time when a PD is detected, customers are, we inform our customer, but unfortunately they couldn't do the shutdown because of some certain RMU or certain electrical assets are so limited, so they can't afford the shutdown. Because shutdown means maybe half day, a portion of the airports have no power. So maybe your luggage belt cannot use or some of the runway cannot use. So they cannot afford that. So they request to wait. But unfortunately, they don't have, after 7 months, this failure happens. So we are being asked, they inform us, we took some photo of the failure, and this become a case study. So, 7 months, you just 7 months the thing happened. So it resulted in unplanned outages. Okay. So looking back into these case studies, we like to really share with you. You see, when I installed the new RMU, for the first year, no PD. Second year, also no PD. Third year, also no PD. But on the 4th year, I start to detect a medium level PD. Then, because I do my PD, how frequent? Every year, right? So every year I'll go. So on the July 2022, I detected PD. But if you look at the curve here below, so the minimum peak to value interval is 7 months. Because by the time I detected, I told the customer, I only left with 7 months. Because the customer said I cannot shut down. I need to wait. Because shut down the airport is a very big thing, Airplane need to come in, so we cannot shut down the RMU. So 7 months We waited, but unfortunately, the equipment cannot wait. It fails by itself. Boom. But from what we know, there's actually 19 months interval. So if there is a 19 months interval, meaning to say maybe in August, the PD really happens, but we are there in July, we did not detect. If we were to detect it in August, then we have this 19 months of interval. And then we can maybe have more time to react. And then, maybe during the yearly shutdown, the airport engineers will be able to, save the RMU, detect the problem, and then try to fix it, and then put back the failed cable termination again. Do a proper cable termination, and then save the switchgear from having a flashover. So that is maximum. So from 19 months, because I do yearly, it shorten the point to failure interval to 7 months. Okay, so if I were to do it on a quarter basis every 6 months, then I maybe by December 2021 I detect. Then I have actually 1 year to do. Then I can also have more time to react. So that is first case study. Okay. The second case study, this also happened in capital city in Australia. So we were actually asked to do PD monitoring. So this PD monitoring, occur. We detected a failure. This was a very, very old switchboard. In fact, older than myself. It's 1975. 1975. I think this if last year you'll be 50 years old, and now this year will be 51 years old. Okay, so a 51-year-old switchgear or 50-year-old switchgear, very old, but because of renewal policy, they are unable to change it. Okay, so but this is a very important switchgear. So the customer have no choice. Say in that case, since I cannot change a switchgear, I better invest in a 24/7 partial discharge monitoring system. So I'm monitoring on a 24/7 basis. Anything happen, I'll be the first to know. Okay, so during all initial PD survey and 18 months of continuous monitoring, no PD was detected on the VT, nothing. So it's very good, near to 50 years old, such switchgear still going strong. However, in 2017, it actually start to have PD. So you see, the owner is very lucky because when we started 24/7 monitoring in 2016, and then 2017 August, the first PD that was actually generated was immediately captured by the permanent monitoring system, because the system was actually polling for data every 2 minutes. So once there's something, 2 minutes later, you will start to PD survey again. 2 minutes later, they will check. So eventually, they were first to detect. So they send an alert. Okay. Once the alert was being triggered, EA, we went down, we take a look. Okay. So we found out from the graph, we can check that PD source raised from 2 dB to 8 dB in a 10-minute period. And then we are able to do a shutdown. So what happened was on the 4th of August, there was a high rise in the sound energy, go up very high. And then it never goes down. And then alarm was triggered. We are there to check, and we confirm this is a real PD signal. We inform the owner, and 2 weeks later, they plan the outages. Okay, so on the 19th of August, they are able to shut down, they rack up the circuit breaker, and that's what you see, burn mark and crack in the insulation. So this one, if you continue to use, basically, you are just waiting for outages to happen. Okay, so we are lucky. So we are able to, rack it out and find it, and then we replace it with a new circuit breaker. Circuit breaker. And then when we put back, we energize back the gear, you can see the signal drop. Okay, so this was fortunately accident being averted. We prevent an accident from happening, a large explosion from happening. Okay, so if you look at the case study, switchgear installed in 1975, So in 2016, when we start talking to them, then they realized that yes, since I cannot change my switchgear, I better do something to monitor it and tell me if it got a problem because my switchgear is already so old. Okay, 2015 is by the time it installed this is already a 40 years old switchgear. So in February 2016, we install, we move on. 1.5 years later, we detected PD. So, this PD signal was detected. Because of the permanent monitoring system, we did not waste any time. We detected the PD once it's actually detectable. Okay. So we were given a longer runway to plan for our next course of action. We are able to have more time to plan. And then, of course, for this case, the owner, is very, very worried. And they say, okay, we try to shut down as fast as possible. So they plan, and 2 weeks later, they plan an outage. They shut down and then rack out the circuit breaker. They were able to see, wow, there's a crack in the insulation and then burn mark in the circuit breaker body. So, so basically, if they were to wait, right, in another 1 to 2 months, maybe there'll be actually a flashover. Yeah. But so they are lucky. But of course, they were actually planning all this with the real data provided and the guidance provided by the monitoring system. So they are able to actually prevent these outages. Okay. So that is another case study. Next, we'll share with you the probability of early detection. So we all know, just like our body, when we are sick, it's good that we are able to detect the problem early. If we were to detect at the later stage, a lot of time we do not have sufficient period or sufficient time to react. So we try to go for early detection. So same for your switchgear, your transformer. You try to detect the problem as early as possible before it fails. Okay. So what are the chances of I detect this PD signal, okay, as fast as possible? Okay, so in EA Technology, with our experience, 60 years in this business, talking, sleeping, eating PD, we observe that the early stage of PD sources evolve over time. It changes. Okay, sometimes you get intermittent source. Today you go there is PD signal. Tomorrow it disappeared. Next week it comes back again. Okay, so the intermittent source can gradually increase in frequency and amplitude until they become constant. Why these intermittent things happen? It can be because of carbon deposit. When you have a hole gap in the insulation, okay, there may be arcing. So this arcing may have caused the carbons to be formed. So when the carbon form, this carbon powder, it actually cover the hole. So when it cover the hole, the PD signal disappeared. But actually inside, the deterioration continue. So as the hole become bigger, the carbon deposit are not enough to cover the hole. Then you see the signal come back again, and this time even higher readings. Yeah. So that is what I meant by intermittent source. And each intermittent source event degrade the insulation. So by the time you found one time, then it disappeared, then it come back again, then the signal will be even bigger. That means the condition of the insulation is even worse. Okay, so intermittent event can be very difficult to detect. You can, because you are not there 24/7. It can actually happen Monday, and then you go on Tuesday, you miss it, and then on Friday it comes back again. Then you will tell the owner, no PD, very good. Yeah, but actually you miss out because this is the intermittent PD. Okay. So this thing will happen if you are lucky. If the failure never happened before you go back again, you can still detect. But sometimes depend also on how frequent you go back to check on the switch gear or onto the transformer before you can detect this intermittent PD activity. Okay, so let's talk about the defect growth rate. So so then you will ask me, so Mr. Andrew, so how can I best detect PD initially? Once it happens, I want to be there to be able to detect it. So we actually plot out a probability of defect detection. Okay, so this model tells how PD defect evolve from initiation to continuous discharge. Okay, the growth rate of course depends on time to continuous discharge, and a shorter time means faster growth, smaller detection window. Okay, and these are some examples that we plot out. So the example scenario assume and initiate PD source with activity from 1 hour per day. Okay, so basically you increase the frequency to become constantly active over 2 to 5 year time frame. Then this model PD source with a variable point to F interval. So how you detect this thing is like, the rates can be different. Sometimes 2 years it fails. Sometimes 5 years it fails. Okay, the chance detection, and then 10 years, then you get you can actually 100% detect. So this time, if the defect is varies from 2 years, 5 years, and 10 years, so we definitely want to detect it as early as possible. So that goes to my second slide. How early I want to detect this PD? First, if you look at my graph, it will be the yearly testing. The first one here. Second, the light blue one is 6 monthly testing. And then, of course, the purple one will be 3 month testing. And last, the green one will be monthly testing. So based on this, we plot out the chart, and then it actually gives us the probability. Okay, example, a 5 year defect model show higher detection rates at 3 month interval. Okay, so if you do annual testing, the first one, you most probably will detect the problem here at 13%. Okay, at the third year. And then if you are doing monthly testing, 80% chance you will detect it at the third year. Okay, so this tell you what? If you do yearly, the chance of you discovering the PD initially is only 30%, very low. But if you go there on a monthly basis, 80% you will capture the PD. Then somebody may ask, how about if I want 100%? Once I got PD, I want to detect. Yes, this solution is now available. We have the permanent monitoring. So this permanent monitoring will detect a developing PD almost immediately. Once the PD is detectable, a permanent monitoring sensor will actually capture it immediately and send you an alert, and then you can decide what you want to do next. But of course, we can't be installing a permanent monitoring solution on all our assets because it's very expensive, right? So that's why we need to plan. Okay, so let's come to the next slide. Okay, you must know how to design a test regime. You must ask yourself, what's your goal? Is it to obtain a high quality PD data while reducing the uncertainty of the point to failure curve? Okay, and then your tradition RCM testing interval is half of the P to F interval, but the HV assets show highly variable P to F periods. Okay, so then you ask yourself, what is a case study? Do I have similar case study for my switchgear? So annual testing detect PD, but shorter interval will allow trending. If I were to go back every 3 months, then I can see the PD. I know the signal will increase or maintain. Maintain maybe means it's not so bad, it's within control, I can wait for a while. But if I go back every 3 months, the signal is increasing, then it's a sign that I need to take action ASAP. Okay. Okay, so just now the case study also show you, a very short P2F in the virtual limitation of periodic testing. Okay, so that's why if we will do periodic testing, we also will miss out the detection of the circuit breaker. But luckily, the owner know that this is a very important switchgear that he cannot afford to fail. He installed a continuous monitoring system, and the monitoring system indeed helped him. Once there's a PD, straight away detected and highlight to him, and then he got enough time. If he didn't shut down within 2 weeks, actually the next another 2 weeks, the equipment will still not fail because because he detect very early, so he got enough runway to plan and take action. Okay, so of course we say all this, but we also need to be practical. We cannot be telling our people every day after lunch you go and do PD survey. No, it's not practical because my people is not just on PD. Right? People need to do something else also. So we must do a balanced periodic testing, or we can consider to install permanent monitoring, especially on those high risk asset, those switchgear that you cannot afford to fail. Once you fail, that means a big portion of your production is impact, or there are big safety issues and stuff like that. So that is one that you may want to consider to install permanent monitoring, because permanent monitoring detect PD every 2 minutes. So it actually tell you the problem straight away so that you got enough time to react. Okay, with that, very soon, I really come to the last slide of my sharing is a conclusion. So the key finding of PD defect detection is the defect growth rate. First thing is it determines how quickly PD defect evolve and directly impacting the detection probability. What type of PD? Is it on a surface discharge? Is it on a internal discharge? Is it a corona? And what type of switchgear? And where am I putting it? Is it in near the river or near somewhere very cold at night and then daytime very hot? Okay, so if that's the thing, I decide. And whether this switchgear is it some switchgear that I cannot afford to fail. If I fail, that means many household will have no power, or my production will stop and I incurred many losses. I have a customer in Singapore. They do semicon, so they're telling me that they do wafer. Your semicon, all the chips are coming from wafer. Wafer look like a disc, and then these are stacked, like 100 per stack, and one disc costs 5,000. So one stack is 500,000. So there are many stack during production. This thing is very sensitive. Once you have an outage and then the production process are unable to complete fully halfway, then this stack of 100 wafer will have to be thrown away. You cannot redo halfway. It's from there start to end without interruptions. One interrupt, the whole process will fail, and then you need to throw away, and then you waste a lot of money. But no choice. If failure happens, this kind of thing will actually incur a lot of losses to the company. So then you decide what type of test interval that you think is worth it. Can I afford a few million within 1 hour of type of losses? If not, then I better do something. Okay, so in Singapore, the customer that I mentioned to you, they believe in permanent monitoring because actually it helps solve a lot of problems, because they have the highest chance of detecting the defect at inception. When the first problem first started, I'm there to pick it up and I tell you what the problem, and then you decide what you want to do. You want to wait, I also can help you because I can trend for you, because I'm permanently monitoring. Every 2 minutes I take a reading. So if the reading is increasing, I know. If the reading is maintaining, then I think I can wait. For 1 month, 2 months, 3 months, up to 6 months, the reading maintains stable. Then I think we can wait. Yeah, but if the reading keep increasing, 1 month, 2 months, wow, from 10 go to 20, 20 go to 30, then I don't want to wait. so then I better plan for a shutdown. Okay, so this will basically give you more information. You can then plan more things. So second, fourth point, due to the different variety in the P2F interval, ranging from days to years, because we won't know. In some, like what I mentioned, a surface discharge can fail your termination within weeks or within days, and then your internal discharge, maybe there's a current CT that have a void in the insulation, they may take years to fail, so you won't know. So you need to know what type of access you are dealing with. Then you plan your testing regime. Okay. So of course, always take into consideration the worst case scenario. What is the worst case if this thing fail? Tell a boss, can you afford failure and then you lost power for 2 hours? Then what are the losses you will incur? Are you able to take the risk? If not, then what should I do? Okay. Last but not least, your optimum strategy. What's the best strategy? Combine your risk appetite and periodic testing. So if you cannot afford failure, because failure actually costs your factory, your chemical plant, your oil and gas oil rig, millions of dollars within few hours, then you may want to consider to invest in a permanent monitoring systems, because they'll be the first one to save you, because it detect PD. Once PD is detectable, so then it will actually save you in a way that it give you more time to react. You can actually plan for a proper shutdown. You don't need to rush, because if you tell your HR, I want to shut down, please ask the people don't come to work on Monday. The HR will look at you and shock, how can I do a shutdown on a Monday? Then you say, because there's no failure. So, it puts you in a very difficult position. You don't shut down, it fails. You want to shut down, the HR say cannot. I don't have enough time to react. All my people all scheduled to work already. Cannot ask them go home. So these are all different things you got to take into consideration. Okay. So with that, I've come to the end of my today's sharing. So, but of course, I'll be very happy to take some of the questions that y'all may have about this P2F failure and what are the planning. Yeah. So, any questions? Please feel free to, post it here.
Thank you so much, Mr. Andrew, for presentation. And before we continue to Q&A session, I'd like to briefly summarize what has been presented so far in bahasa ya. Jadi pada sesi hari ini kita telah mendapatkan pemahaman yang sangat baik mengenai bagaimana partial discharge dapat menjadi indikator awal dari degradasi insulasi pada aset tegangan tinggi. Kita juga melihat bahwa tantangan utamanya bukan hanya mendeteksi adanya partial discharge, tetapi memahami seberapa cepat kondisi tersebut dapat berkembang menuju kegagalan. Dan melalui berbagai study case yang tadi sudah di-sharingkan oleh Mr. Andrew, semakin jelas bahwa pendekatan monitoring yang tepat memegang peranan penting dalam menjaga reliability aset. Dan melalui penjelasan mengenai PD Continuous Online Monitoring, kita dapat melihat bagaimana teknologi ini mampu memberikan visibilitas yang lebih baik sehingga keputusan maintenance dapat dilakukan secara lebih proaktif dan berbasis data tentunya. Karena PD itu benar-benar seperti kata pepatah Indonesia yang bilang hari apes tuh nggak ada di kalender, tiba-tiba equipment failed aja. Nah, jadi kita sekarang lanjut ke sesi tanya jawab, dan sekarang saya sudah melihat banyak pertanyaan di kolom chat. Namun pada sesi webinar hari ini saya akan memilih 4 pertanyaan saja. Dan alright, Mr. Andrew, now we will move into the Q&A session, yeah. And I can see several questions already coming into the chat box. And at the moment, we choose 4 questions in the chat box.
Okay.
And you can answer a direct question, yeah. First question comes from Mr. Adi Setiawan. And the question is, which factors determine the shape and length of the PF curve for a partial discharge defect?
Okay. That's a very good question because that is also the question I asked when I first, so go back to this one, right? Uh, is it this one?
Yes.
So can you repeat the question again? Yeah, sorry.
The question is, which factors determine the shape and length of the PF curve for a partial discharge defect?
Okay. So the this length and the curve, all this, right? There are a lot of factors. But of course, there are some main type of factors. Is like once you detect PD, so first thing is what type of PD? The like what I've been sharing. If it's a surface discharge, then the curve, the P to F will be very short. So why? Because that's the characteristics of surface discharge. Once you have surface discharge, you hear loud crackling sound. The P to F interval will be very, very short. Sometimes as short as a few days, but typically a few weeks. So this is the first thing. And then what other factors would be the type of PD, and then of course the type of assets you're looking at. If it's a cable, then is it at the termination? If it's at the termination, then also depend how severe it is. So to answer to the question is there are a few factors. First is what type of PD, and then when you detect it, what type of PD is, what type of asset it is, and what type of environmental, what type of environment, and then also the condition of the switch, the switch gear. Is it a new switch gear or old switch gear? And then but sometimes this can also be irrelevant because I give you case study. 4-year-old switch gear have failure. But of course, we know the reason is because of the cable termination never changed. They use back the old one. So these are the few factors that can affect the P to F interval from very long to very short once you add in all these factors. So a lot of time it depends on but to counter this problem, right, there's always a thing that we can do, which is called trending. We can trend. If we really cannot take action immediately, then I think trending will be the best thing that you can do. You try to collect data as close as possible, and then how bad, what is the condition? Is it deteriorating or is it maintaining? So then you actually can give you a better idea of your P to F curve, the interval. Okay, I hope I answered the question. Yeah.
Yeah. Thank you, Mr. Andrew. And the next question is coming from Mr. Fatahillah Muhammad.
Okay.
Yeah. And the question is there any formula to know when failure happens after we found the P?
Is there any formula
Yeah.
we found PD?
Yeah.
Okay. So the answer is no formula. Yeah. So as of today, I think there's no one. It's just like the heart attack example. The medical, industry or society has been spending a lot of time studying about heart attack. But today, no matter how advanced the problem, uh, the doctor will not be able to tell you when you will have heart attack. He only can tell you, hey, you got heart attack, you got heart problem, you may have heart attack. So maybe they say then you need to do something, go for surgery, change. But no doctor will be able to tell you, hey, tomorrow you have heart attack at 2 o'clock. So you be prepared. So there's no, even the best doctor today cannot tell you. So it's the same for PD. PD, we won't be able to tell you, when the failure will happen. Yeah, so that's why I give the example when I was a young engineer, I was shocked when one of my senior engineer told the customer, when the customer asked when my instrument will fail, then he said, must ask God. God will tell. Only God will know. I don't know. So but to answer the question is at this point, there's no formula. We are unable to calculate exactly when you feel, but we, based on our experience, based on our knowledge on and then based on all this point that I shared just now, like type of PD, type of asset, whether the amplitude and what type of installation and the environmental condition and the physical position, where you put your substation, all this adds up, and then we roughly can tell you how how fast or when you think the failure will happen. Yeah, so that's why I can say if a surface discharge is a few weeks, even few days, but I cannot tell you 3, 2, 1. I don't know, because it's only when we see the problem, we hear the problem, then we know how severe, how serious, then we know we can make a judgment call. Yeah. So that means going back to the same thing is every PD is unique. So we will not be able to have a fixed formula to count the P to F interval. Yeah.
Yep. Thank you, Mr. Andrew.
Hmm.
We are going to the next question, yeah. The
Hmm.
third question coming from Mr. Suheli. I'm trying to translate, yeah, the question. If we are performing a partial discharge test on 6 kV switchyard cubicle located close to a high noise environment, such
Hmm.
as a turbine or generator,
Hmm.
will the high level of background noise affect the PD measurement result?
The answer is definitely yes. The high background noise will definitely affect your reading. So it depends on. Okay. So the whole thing is so to answer this question, yes. But I think I'll just add on a little bit more on how you should counter this problem. So how do you counter? You are there. It's a very noisy environment, but you definitely need to if you check on the condition because your boss asks you to go and check, or you are paid to go and check. This customer say, I want to know. So what will happen is you need to, first thing, as a PD practitioner, you are there to do a PD survey, you should be able to know, you detect what is the ambient noise and the metal noise. Okay, so that's what we always teach the student during the PD training course in the very noisy environment. So then we also try to find where the noise source come from. Okay, so that because every noise source, there will always be a signature, the pattern, like what I shared initially in the beginning of the presentation. The different type of PD have different type of waveform signature. So we try to identify this type of signature first. So with the identification complete, then we go back to the, let's say the switchgear that we are tasked to do the PD monitoring. We want to see whether is this real PD or not. Then we'll then use the instrument, the different graph, like PRPD to detect and see what is the waveform. So unfortunately, sometimes it can be very high. Now I've been to certain place, like in a power plant, those using natural gas to power one. It's very high reading because besides there's a generator or what. So what will happen is we are unable to shut down the generator because you cannot shut down so no choice. So then we got to basically determine where the source of PD come from, which direction, and then where is the signal characteristic by plotting out the PRPD plots. Then from there, when we take a PD at the switchgear, we can actually compare. So if the signature is the same pattern, then we can roughly tell that the high reading we are getting is actually a noise coming. But of course, today the industry has changed, evolved very fast. Even I detect, right, I can straight away decide this high reading is it coming from the switchgear or actually is the noise being coming from a generator, because we have this thing called the location probe. So this location probe help us to know where is the noise coming from so that we will not make the wrong to avoid making the wrong judgment when doing the PD survey. Yeah. So that is the few things that we'll do to make sure that we are not being so-called affected by this high noise, or we make sure that we detect the thing and we won't be giving it a false reading because of the high noise. Yeah. Oh, so that is to answer to question.
Yep. Yep. Thank you, Mr. Andrew, for the answer.
Okay.
Yeah. For the last question ya, Mr. Andrew, atau ada Bapak Ibu yang mau bertanya langsung kepada Mr. Andrew mungkin? Belum ada. Saya izin melanjutkan membacakan pertanyaan yang terakhir ya. Tapi mungkin untuk pertanyaan lain yang belum terpilih untuk dijawab saat ini, kami akan menjawabnya di waktu yang berbeda. Jangan khawatir, setiap pertanyaan akan kami catat dan akan kami jawab di waktu yang berbeda ya Bapak Ibu. Oke, Mr. Andrew, for the last question from Mr. Saiful from CFPP 350 megawatt in West Java. The question is, which is better for detecting PD offline test or PD online monitoring that install permanently? What the pros and cons from them?
Okay. All right. So for PD offline testing, first thing I'll talk about the pro and cons between online and offline. Offline, of course, got to first do a shutdown. I do a shutdown, then first thing is the whole shutdown process can take a long time. If I want to shut down, I want to test a cable, I must de-energize the cable, take out the cable termination, and high pot. So to test a cable that is offline, it can take me half day, because of the preparation. I need to take out the cable and do that to test. But yes, offline testing will be more accurate because I inject the voltage and then check the PD. So offline pro is the more accurate because there isn't the noise factor affecting your reading. But the con is you take very long time to prepare just to do this offline testing. The setup is very tedious. So you compare if I do an online testing of the cable, using the cable as an example, it takes me only 30 minutes maximum to do a testing. So the pro and con is the timing. Of course, definitely offline, I would say is more accurate than online because it takes away all the unknown factor like noise, from the instrument and everything like that. Yeah, but if you ask yourself, I have hundreds of cables to test. So what should I do? So do I take 100 days to finish, or I can take maybe 100 half, less. 30 minutes I can do one cable. So one day maybe I can do 6 cable. So maybe 10 days I can finish the 100 cables. So then you go back and ask yourself, what should I do is best? So in today's context, right? I work with a few power utilities. Again, using the 100 cable as an example, what they'll do is they will first do the online testing first because it's difficult to shut down, and then shutdown require a lot of process. So they do online testing first. They'll check. So if certain switchgear or certain cable they detected PD, then there are a few things they can do. Either they can do a permanent monitoring. When I say check, it's a snapshot. I'm not talking about monitoring. Monitoring, there is a second step. Then they will put monitoring to detect. But if they don't want, then they can do straight away go to offline to double confirm. Meaning to say, I'll do online testing for my cable, all 100 of them. So those that I have detected PD, I will confirm again with an offline testing. So that is the practice that I'm aware of some power utilities are using. Why they do that is because so that they can comb the highest number of cable in the shortest time possible, and then they go back to those that have problem to double confirm where is the PD, and then solve the problem. Okay, so to answer to the question is, both have their pro and cons. Yeah, it just depends what you want to achieve. If you got the resources, you can only want to do one cable, then you can do offline. If it don't impact your business, your impact your your output, then yeah, offline is good. Yeah, but if you today got 100 cable, then maybe you want to think again. Offline maybe too tedious, too much effort, too much time. Yeah, so I better try to comb as many first. So I use my online. That's the reason why online has become more and more popular. And then online with your permanent monitoring, right? It actually makes you able to detect the problem faster. Yeah, and then give you alarm in the shortest possible time, and then you got more time to plan. So that's why I will not say who is it, but for businesses, for utility, definitely going for online help to solve a lot of problem. Yeah, then offline is for you if you want to verify the problem, you want to confirm there's really a PD and where is PD, then offline will be a very good test. Yeah. Okay.
Question. And I think we have now come to the end of the Q&A session. And thank you once again, Mr. Andrew, for addressing all the question clearly.
Thank you. It's my pleasure.
Oke. Dan Bapak Ibu sekalian, kita hampir sampai di penghujung acara. Semoga pertanyaan-pertanyaan tadi sudah dijawab, bisa diterima dengan baik. Jika nanti ada pertanyaan lebih lanjut, kami PT Tiara Vibrasindo sangat terbuka untuk diskusi lebih lanjut setelah acara webinar ini ya. Oke, seperti yang saya sampaikan di awal pada webinar hari ini, kami PT Tiara Vibrasindo menyediakan giveaway untuk 4 peserta yang beruntung sebagai bentuk apresiasi dan partisipasi aktif dari Bapak Ibu sekalian selama webinar berlangsung. Dan peserta yang masuk dalam undian adalah peserta yang aktif bertanya selama sesi webinar serta peserta yang telah mengisi form feedback yang dibagikan oleh panitia di kolom chat. Jadi jangan lupa setelah ini Bapak Ibu bisa mengisi form feedback yang sudah dikirimkan oleh